Okay, so yeah, let me know if you have any questions. Let's do us here. So the plan was, yeah, we'll finish off the decision tree stuff, talk about that a little bit, and then maybe jump into the current assignment. So most of the assignment six, for everybody who's listening, if you haven't looked at it yet, is really kind of the next chapter after the decision trees. So a major part of it is actually kind of just using some different ensembles besides decision trees, so random forest stuff like that. But then also I want to talk about we still have um, the yeah, you still have until next week to work on that. So I'm not certain why it's showing up twice on the calendar here. So we're still working on the decision trees and the ensemble learning this week and next week. So, oh, so I need to check my announcements too. I don't know what happened to. So yeah, we were supposed to be working on the Unit 12 stuff starting next week, and we're doing the Unit 11 stuff on decision trees this week, and the assignment session will be due next Friday. We still have time to work on it. But yeah, as I started saying, I was going to get started looking specifically at the assignment six today a bit. Because it's mostly about the stuff on ensemble learning. So maybe we'll start talking about that. But in particular, the last part of it is building a stacking ensemble by hand, which sometimes in the past we've used this assignment. Some people need a little bit of hints on that one. So I don't know if we'll get to that today, but yeah, I'll just let people know about that, so kind of be aware of that. If you haven't started on the assignment six, you definitely should get started on. I am working on getting the assignment fives turned back. So hopefully, I think almost everybody had submitted the previous assignment, so should get that back here soon. I hope. So check here. Okay. So I didn't have a whole lot more to talk about on the decision trees. I'd mostly stopped because we got through most of the basics of that last time. We don't really go into it too deep about how it actually works. But yeah, if you read the textbook, so just to kind of summarize a little bit from Tuesday, we had talked about how the decision tree works, and in particular the algorithm that's used to actually build a decision tree. So a little bit of notation, but you can think of this as a cost function. It is basically the same idea as a cost function like we used for linear regression and other parameterized models here, although it works in a greedy way. So we actually build up a tree incrementally. And you don't have to get too caught up on the details, but the idea is that this is able to pick at any given time which parameter and then which threshold on that parameter is going to minimize this here. So we are minimizing this, so it'll give us the lowest Gini impurity measure or whatever measure we're using for how well separated or not separated the categories are at this point. So just taking that idea, this will be the one that splits it and gets the minimal basically weighted average of what the resulting Gini or whatever measure you're using is for the two nodes after you split it on that parameter at some particular threshold. So So yeah, the last thing we talked about on Tuesday is that that is done iteratively. So it's an example of a greedy algorithm. In theory, you could come up with a cost function in order to figure out the best tree overall, but that ends up being having basically an NP complete problem. So it's an exponential cost time to try and minimize a decision tree globally. So in practice, just doing it incrementally gives you decision trees that are going to be pretty good, going to be pretty close to what you'd end up getting anyway, at basically like a linear cost in order to create a decision tree using this kind of greedy algorithm, the cart algorithm that's discussed here. So yeah, whenever you're fitting a tree, like in scikit-learn, it is basically using that method. So, when we did our examples to fit using a decision tree classifier, behind the scenes it's going to use that some version of the cart described there. So the resulting trees that we get should be that the parameter that was selected here will give you the lowest cost, and then we just keep doing that further down until we either reach leaf nodes, can't go any further. So once you get down to a Jenny of 0, you can't actually continue past that point, or we have some other regularization. So we limit the max depth or do some other things. So I usually don't talk too much about entropy. I don't know if there's other. I mean, I'm sure you could come up with other measurements as well. You can let's see. Rerun this notebook here, but let's look at if there's any other criterion that scikit-learn allows. So yeah, so also you can use log loss, entropy, Gini, or this Gini impurity that we talk about. So I mean, from my experience, usually you could try it. There are probably some problems where you might get a better classifier using one or the other, but usually try all three of those, you get pretty much the same performance in terms of how well your classifier will do or decision tree. So entropy is a kind of a classic measurement of the amount of information. So if you've ever seen that before, it's really the same thing that's being used. Use that one. So you notice that in this notebook, but we will get different decision boundaries. So in this case, we use the entropy measure. So I decided to use petal width for the first. So again, I might have these mixed up. I thought we fixed those last time. So our tree is showing petal length and then petal width. Yeah, not certain why. That doesn't seem to match what I was expecting there. Just real quickly try and rerun. So if you're looking at these cells, I mean, we should be, we're refitting a tree here. We're actually re-exporting it to a new figure. Oh, I know these notebooks. When you're using these figures in line, so all we're doing in a markdown cell is we're actually using kind of HTML notation here, so hypertext markup to insert a figure. But yeah, those don't get updated unless you reload the page in your web browser. So it might be that might be what confuses me. So let's see if we reload this like this. So yeah, there we go. So I think that's what was happening. So sorry about that. I mean, I guess that's in general kind of a good thing to point out is that the way that these figures are shown, it doesn't update them immediately. So even if you reopen the cell and hit Shift Enter, it might not reload the image. It'll keep like a cache version of it. You might have to reload the page. So that's kind of what I was expecting there. So when it did the entropy, by that measure, it just decided to split by, instead of the length, it split the first time on the petal width here at the 0.8, and then did another one when we limited the depth there. But still, in terms of how well it performs, you'll get basically about the same performance on predicting the data that you create the tree with, or predicting unseen data. Entropy, rigidity, purity, or probably even the other one, the log, linear log measure. So yeah, also, I just mentioned the last few things here. So there are others. I mean, I guess the general conclusion about decision trees, they're not really considered state of the art. I mean, you're not going to be able to build a classifier that will compete with a neural network or something like that, or even support vector machine using a basic decision tree. But they are, they're good basic ones, so they make good sort of baselines. Try a decision tree, or like a k nearest neighbors, like we talked about, just to see, okay, what can I expect at least at a minimum that I ought to be able to get on performance in terms of a model that can say predict, how well it can predict my set of data, and then you can take that as a starting point and try and improve from that, right? So, but also, if you've read the next chapter after this one on decision trees, on basic ensembles, if you combine multiple decision trees and have them built, put some randomization in there, decision trees actually can get pretty close to being state of the art. I mean, they can often, in many instances, many kinds of data sets, even relatively big data sets, give you good performance, almost as good as you might be able to get with anything else sometimes. So for that reason, it's good to understand a basic single decision tree, how it works. So we up in the notebook up to this point, if you read through it, we only used limiting the depth of the tree. So the only way you can regularize decision trees is by limiting different things. So you can limit the tree depth. There's other ones you can try. And again, from my experience, these often, will give you similar results. There are probably some problems where doing one thing versus a different thing will give you a much better result. So, you just have to kind of either, use like a grid search where you're trying these different ones if you suspect that might be the case, or yeah, or be familiar kind of with the problem and have some idea of why, changing the limiting the leaf nodes instead of just the depth might be better or worse. Sure. Most of these should be self-explanatory. So another thing, I mean, I think I mentioned this on Tuesday, but it is good to make sure that you understand that the default behavior of a decision tree is that if you don't limit it, it is always going to completely fit the data that you train the decision tree. Okay, so by that I mean it will always, if you let it go all the way down to leaf nodes and a Gini purity of 0, it will. Just a second. I need to answer this. I will be back. Just one second. Um, So yeah, so let me just wrap up talking about decision trees here. So the last point I was going to make is that yeah, decision trees by default are going to always overfit the data. They'll always give it so they give perfect predictions on the data that you fit it with, that you apply the CART train algorithm. If you don't apply some regularization, so that's one thing you should always keep in mind with decision trees. And the other is that, I mean, you know, so in order to actually get good performance with the decision tree on unseen data, you do have to use at least one of these, if not multiple of these. So besides limiting the tree depth, you can just most of these hopefully are self-explanatory. So you can give the maximum number of nodes, leaf nodes that you end up with, and they'll stop as soon as the tree has reached that number of leaf nodes. So for the features and the samples, you can, some of these are, good to be familiar with, because these are usually what decision trees on ensembles are playing around with, like the samples or the features. So just probably the easiest to understand is the max features. The decision function, the cost function that we gave before for the CART algorithm, we're implying that we're considering trying to find the lowest one for all features. So K can be any of the features, right? So, in this notebook, we were only using 2 features from the iris data set, but in practice, you're going to have hundreds or thousands of features if your data set is a real kind of data set, right? So the CART algorithm will consider all of those and consider the threshold for all thousands of features that you have on your real data set to find the one that will give the minimum cost when you split that node. Right? So you can add some randomness into the tree by limiting the number of features that are evaluated for each split. So when you're doing stuff like this, another thing is that mostly your trees are going to be not completely, but they'll be fairly deterministic. So by that I mean that you would get the same split because there's not any randomness going on. So you get the same tree. But when you start playing around with these, it's going to only consider some number of features, so not all of them. So it'll pick some set of features and then split on the best one just for that subset. When you use max features like that, right? And the subset that it picks is going to be, I don't know exactly how it does it, but it's going to be some random subset of the total number of features that we have. So when you use this, you should expect that you will get different trees. But there's some randomization that'll go on there. So unless you set your C or something, each time you do it, a different subset of features will be used, and that could cause significantly different trees to come out of the algorithm creating the decision tree. So, okay. So, but yeah, there might be some others, that can be played around with for decision trees, but these are the ones that are often used, besides the max depth for the tree as well. So yeah, I guess another thing in general to know about decision trees, because of the way they work, you're really only going to be getting finer and finer kind of decision boundaries that are orthogonal to the direction of your features. So what that means is when you plot out, like we're doing here, some sort of a map in order to visualize where the decision boundaries end up being, they're always going to be at kind of right angles to the feature dimensions that you're splitting on. So that has some possible impacts on performance. That is discussed a little bit in our textbook when it talks about regression here. So we'll probably get back to that in seconds. So the result is, if you look at it, you see something like this. So this one we switched just using some made up classification data using the Make Moons data set, which I think we've seen before. So here there's no real clear line, and we're just regularizing. In this case, we're not regularizing at all. So by default, we should end up with a relatively, potentially large tree that will go on until it's able to perfectly classify each data point. So you see that it kind of wiggles around and stuff, even to the point where some of these are just to get the last sort of point that we train it with on the correct side. Another thing about these is we probably don't have the grid size small enough here. So it probably really does also have some boundaries around all of these, so they're all correctly on the positive class. So what you expect then when we're talking about regularization, like if we're limiting the depth of 4, is instead of getting all kinds of stuff around there, so that every point when you get finally down to it is going to be on the data that you fit with is correctly classified. It'll stop much sooner than that, so you get a much cleaner line. Right? So remember, this is just a general kind of comment about how regularization works in these kinds of models. Is there's always going to be noise. So like on this Make Moons data set, it could be that these are noise or even errors, points that were misclassified and stuff like that. So if you go too far, your model might not do as well to generalize on data it hadn't seen before. So all of those parameters we're looking at that limit the tree to stop before it gets all the way down to leaf nodes will tend to then, if you look at the decision boundaries, it means that there's much less of them. They're much cleaner. So when we limit that to 4, you get something like this, which is kind of pretty closer. So if you think about how like a nonlinear support vector machine would do that, it would be in a similar kind of area, similar sort of decision boundary on this sort of data here. Okay, and then finally, you can actually use decision trees for regression. I don't know if these are really that useful in practice. Decision trees sort of makes sense to me anyway, much more for a classification task. But there is a decision tree regressor. The way to think about this is that over the way it works, if you're doing it for regression, is it's going to split up the problem into small ranges and will give the best linear approximation over those different ranges. So in practice, what that means is it looked something like this. So if we have in this case, it was like a quadratic function that we added some noise to. Yeah, so this function, so this is kind of similar to what we had done in our assignment where we were using a hidden function of some degree, but so here we're just using something to the power of 2 and adding some noise to it. Right? So the true function is a parabola here. So using a linear tree as a regressor, it's going to kind of end up basically splitting up into parts, giving the best sort of linear approximation for different ranges. And if we didn't have any regularization here, we probably did that. So if you loosen it up like that, yeah, with no restrictions, again, it would perfectly fit the data. So this also maybe gives you people a little bit of idea of what it's doing for classification as well. Right? So with no limits, no regularization, so no limit on like the depth of the tree or whatever, it splits it up so that every one of these points is exactly in some range. And we're going to have a prediction when we get down that leaf node that the range that we ended up for that point is exactly whatever the regression point. So what it looks like in practice then is something like that. So kind of like when we're overfitting for like a linear regression, with no regularization, similar thing is happening. Decision tree will get down to every point that has a single range in a single leaf node. But this would again tend to be pretty bad for unseen data, usually. Okay, so see here. Let me go ahead and let's switch to the assignment 6 for a little bit. So I'll get started just looking at the tasks on that. Then I'll mention a few things maybe about ensemble learning, but we'll probably leave it till next week to actually get into ensembles like force and stuff in more detail. Let me go ahead and my assignment here and bring it up. So yeah, as usual, that might take a little bit of time to get it set up here. So yeah, if you haven't started assignment 6 yet, just a couple things about it. So I mean, everybody should be familiar kind of with the format by now. We have yeah, I've still gone back to I kind of gave you stubs for all these, so we're kind of back to what we were doing at the beginning of the course. I haven't modified this stuff yet, so you should be able to just you won't have to uncomment the things to import the functions that you're going to be implementing, nor uncomment the lines in your notebook for the assignment that are going to try and run the tests. We are using this data set. So just a little bit about, it's a little bit bigger than some of the toy data sets we've been using in previous problems here. It is a classification. If you're interested, it's from the from this set of repositories here. You can get like the data dictionary, which is kind of a description of the things, of the features, and other stuff if you need a little bit more information about this data set here. So, but yeah, I did, the fetch OpenML is a built-in method for scikit-learn, but I did ask you to use that. You can use that to load any of these data sets from the OpenML repository, just by, hopefully I get enough information on there to figure out how to specify which one you want to load there. So you might have to look through the documentation to fetch OpenML. But yeah, there's a bit over 19,000 samples in this. It's a binary classification data set. It's a little bit skewed, which I don't remember if we've talked a lot about this. So one thing that can be difficult when you're doing a classification problem is if you have one category that's for the data that you have available that you want to make a model with, you want to train with. That where one category has much more instances than another, or like if you have a multi-class classification, if you have one category that has a lot fewer instances than in the others. That can make it much more difficult both to evaluate, but also to get a model that performs well on the data. This one is too bad. So we've got about 2/3 in one class and 1/3 in the other. Yeah, this data set had 10 numeric features. There's no missing data or anything on that. So once you load it, you don't have to do any other kind of cleaning with it. I think one thing, you have to be careful that you correctly assign the, so you do have to encode the Y or the label here using like an ordinal encoder. Be careful to do it the way it's described here. I mean, if you don't do it the way it's described here, you probably won't be able to pass these tests. But the positive class is supposed to be G, and the negative class was the other one, the H. Yeah. So yeah, I mean, this is if I remember right, this was used in some competitions. Although I think this data set was actually a synthetic data set that was created to be close to an actual real data set of some astronomical observations where they were trying to build a classifier to detect or not whether there's a signal using these 10 features here. Another kind of heads up on this assignment. So there is a function that we will be needing. See if there's a function that we'll be needing in order to split the data, we are going to be making use of training and test data. Not only that, though, we need a three-way split this time. So in particular, when we get down to the last task where we're building a stacking classifier, we're going to need 3 different splits on this data to do it correctly. So this isn't meant to be a real big challenge, but the idea, if you read the description, is to go ahead and use the train test split, but just use it twice. There isn't a function that will give you like 3-way split as a default in scikit-learn, but you can easily just apply basic train test split twice to get training data, validation data, and testing data. So yeah, you're supposed to use parameters and give back the data for these absolute sizes that we specified. So we have like 19,000, a bit over 19,000. So by this split, we're going to have a little more than half of them in the training data, and then of the 9,000. So left, half of those in validation, and then the last 4,500, a little bit more than 4,500 in the final test data set. Assignment 6 is finally up here. Go ahead and actually open up the actual notebook here. So yeah, let me just describe a little bit the tasks 3 and 4 for the last 10 minutes that we have here. So we'll talk more in case anybody needs to get a little bit more discussion about ensembles. We'll talk more about these next week, or of course you can read through our textbook materials and the notebooks for the class here. So the basic idea, so in this assignment, you're going to get a lot of practice building some classifiers. So you really have to build some individual regular classifiers. Some of these we've seen, you're familiar with, we talked about k-mesh neighbors, logistic regression. So all of these are going to be built as individual classifiers that support vector classifier. Decision tree, actually, we talked about all these except for multi-layer perceptrons, which is really a neural network. So that's the course. If you're interested in the summer here, we've got a course on neural networks and deep learning where we'll go into kind of details of doing neural networks. But yeah, all the others we've kind of seen in this class. So the idea of an ensemble, real quickly, is one way to do an ensemble is to build individual classifiers and then so train them like you're familiar with, like train them on the training data that we get with the split, which is what you're supposed to do here. But then you ensemble them, think of it as like a vote, right? So each of these, since we're working with a binary classification task here, each of them is just going to, for a new set of data that you want to classify, is just going to give a true, false, or a yes, no answer. Right? So the simplest for a binary classification for an ensemble is think of it as a vote, right? So the majority wins. So if you have 5 classifiers, if you train them on the same training set data, and then you ask them to make predictions on unseen data, whichever 3 or more classify it as one way or the other for binary classification, you would specify it, that you would use that as your prediction overall for the ensemble. So, I mean, really, ensembles are relatively easy for most people to understand. Really just a collection of a bunch of different classifiers. It's a little bit more complex to combine them, right? So it's clear for binary classification. You can do like a simple majority vote. It's a little bit, although of course, what do you do if there's a tie? So if I have four instead of five, and two for one and two for the other, you have to break the ties now. The other basic kind of problem on the ensemble is, okay, for multi-class classification, again, it gets more complex. So if you have 5 classes and I have 5 classifiers, so each vote for something else, again, maybe the majority vote is a little bit too simplistic, won't always work well. But yeah, I mean, that's really what I've been describing is really a hard ensemble. It's just a kind of majority vote. If your classifiers can also give some estimate of the probability or have some estimate of how sure or unsure they are about their prediction, you can use basically a weighted vote, or that's kind of really what the soft voting ensemble does. So in order for this to work, for the second part here, for the task, you have to use classifiers that all support in scikit-learn the method to also return back the probabilities for your prediction for each class instead of just the final answer, whether it was yes, no, or a binary. But yeah, assuming you can get an estimate of how certain or uncertain each classifier is in its prediction, you can basically use sort of a weighted vote. So weight each one's by how certain they were on their answer when you're combining. And then finally, I hinted at this. So the most important thing maybe to understand about the ensembles really is this idea of random forests or extra trees. These bagging classifiers. And I guess I am getting a little bit into some of the stuff that I was going to talk in more detail next week. So another way to do an ensemble is instead of having a bunch of classifiers in all different algorithms, like you do in task 3, you can't imagine just training a bunch of classifiers using the same algorithm. So a bunch of decision trees. It's the basic way that a random forest is done. Okay? But of course, that doesn't really help you if you train them all, and they're all end up being exactly the same. So you have to train them so that they have some randomness in there. So basically, like the idea that we were talking about, if you limit the number of features that are considered, you end up with very different looking decision trees, right? So if each step, if I have, we have 10 features in this assignment, the 10 numeric astronomical observations are being used as features here. If you limit every decision to only use a subset of 3 features or something like that, I could create a bunch of trees and they'll all be quite different. Another way is you could also limit them so that I create trees where I train them only on a subset of the data. So, we've got 10,000 data in our training, 10,000 samples in our training set. We could limit it so that if I want to create 100 trees, each one is only trained on 1/100th of the samples. That's the example of limiting the samples. So anyway, for these kinds of bagging classifiers, you have to have, you use all the same classifier. It doesn't necessarily have to be a decision tree. Decision tree. You could use a bag of support vector machine, support vector classifiers, or other things. But traditionally, a collection of trees are used because they're pretty easy to randomize. So that the result is that each one of the classifiers, even though you're using the same algorithm, see different parts of the data, or they can do better for some subsets, and other decision trees will do better on other subsets. So as long as you get a good variety, each individual one might not perform well, but the collective decision by combining a bunch of them will perform good usually. In fact, I already mentioned decision trees are surprisingly effective on some types of data sets. They'll perform as good as anything. Neural networks, deep networks, for some kinds of big data sets. Okay, anyway, so that's what task 4 is. So I'm going to leave it there for today. So like I said, next week we'll get into more details of these ensembles, and especially random forests. And also, I didn't say what an extra tree was, but we can talk about the difference between the random forest. Extra just stands for extremely randomized or extra randomization. So, and then also, yeah, next week we'll get into details of what a stacking classifier is, and this last task here, how we're going to be creating it. All right, yeah. So did you want to bring up anything before we kind of adjourn? Let me see. Yeah, didn't have any questions from the audience. Oh, sure. Let me go ahead and stream then.